There's two other convergence tests you might remember from calculus: the ratio test and the root test. I'm gonna state the two theorems here. I'll doodle a proof of the ratio test, and the proof for the root test is basically the same. Suppose you have a sequence of positive real numbers. Then, on the one hand, if the limit when n goes to infinity of the ratio between the n+1 term of the sequence to the anth term is smaller than 1, then the series converges. Now, in order for this to make sense, it's not enough here that these numbers be non-negative. They have to be positive, otherwise you'd be dividing by 0. Okay? But if that happens, you can always start after the last time where a term is equal to 0. And you can think of it as, if you keep on adding zeros, you might as well just remove the zeros and renumber the terms of your sequence. If the limit of the ratio is greater than 1, then you know for a fact the series diverges. If it's equal to 1, you can't say. You have to use some of the test to determine if the series converges or not. This version of the test is a very strict version of the test in the sense that there's another version that uses the limit superior and the limit inferior to say something about convergence or divergence of the series. I'm going to prove it just for the limit. It's the same sort of idea in both instances. The statement for the root test is the same. You just replace an plus 1 over an by an to the power 1 over n. Before I prove this, let me discuss the convergence of one specific series. Does the series 1 over n times n plus 1 converge? Well, it will converge if the sequence of partial sums converge. So we're interested in computing this limit here, right? We sum up first k terms, and then we let k go to infinity. That's how we know if series converges or not. That's the definition of convergence. Assuming for the time being that the limit exists and so that we can write this thing, it's useful to see that we can rewrite 1 over n times n plus 1 as 1 over n minus 1 over plus 1. And this is useful because this is now a telescoping series, and all the terms cancel out except for the first and the last term. This would be the limit when k goes to infinity of 1 minus 1 over k plus 1. So 1 minus 0 is 1. So this series here converges. You can say a little bit more. We know exactly what it converges to. It converges to 1. Well, here's another example. Does the series 1 over n squared converge? Well, here we can use the comparison test that we saw in the previous video. 1 over n times n plus 1, that's always greater than or equal to 1 over 2n squared. But if you work it out here, you get n squared. Right, if you work it out here, what you're getting is 1 over n squared plus n. And what we do know, 2n squared is going to be greater than n squared plus n for every n. But I mean, it's not difficult. Bring the n squared to the other side. You have that n squared is greater than n for every n. Is that the case? Well, it is. Again, you might want to show this by induction, but at some point this is something we've left behind. We don't prove these things unless you're explicitly asked to do it directly. That we can take this one for granted. So the 1 over n times n plus 1 term of the sequence is always greater than 1 over 2n squared. Everything here is positive. If I do the sum of all these terms, the inequality has to be preserved, and I know that this thing is equal to 1. It converges. Hence this thing has to converge as well. So what I know here is that this converges. If it converges, then I can take the 1 over 2, which is a constant term, and put it out. So 1/2 of the series 1 over n squared converges, hence the series 1 over n squared on its own converges. Let's prove then one of the directions for the ratio test. So we assume that the limit when n goes to infinity of an plus 1 divided by an is equal to some quantity which I'm going to call q, and this quantity is smaller than 1. Let r be the midpoint between q and 1. So this is where the ratios converge to. It's smaller than 1. By assumption, r is going to be the midpoint right here. By construction, r is strictly between q and 1. But what we do know here is that there can only be finitely many n for which an plus 1 divided by an is greater than r. If that wasn't the case, if there were infinitely many indices n for which an plus 1 divided by an was greater than r, then q could not be the limit. Because if you were to pick a small enough epsilon neighborhood around Q, you wouldn't have that all of the ratios would be in that neighborhood after a certain threshold n epsilon, right? So you don't have a choice. There can only be finitely many such indices. So you can find an index n such that whenever n is greater than n, an plus 1 divided by an would be smaller than or equal to r. But in particular, if n is greater than this threshold capital N, then you can rewrite the nth term of the sequence an as an over an minus 1 times an minus 1 over an minus 2 all the way up to a capital N plus 1 divided by an times an. Now, does that make sense? It does, right? Because all of these terms cancel out. You're left with an an alone. So yes, okay. This is a meaningful statement. It is meaningful because, by construction, each of these is smaller than r, because we're using indices n that are greater than capital N. So what I have here is that this is smaller than r, this is smaller than r, they're all smaller than r, then I have this term an, and how many of them are there? Well, there's going to be n minus capital N. Let me just look at the tail of the series of interest. This is going to be less than this because each of the terms an is smaller than a capital N times r n minus capital N. I can rewrite this slightly differently as the following series. Now this is a geometric series, right? R is smaller than 1. Now it has to be greater than or equal to 0 as well because the terms an are all positive. And so when I look at the ratio an plus 1 over an, these all have to be positive. And since these converge to Q, Q has to be positive. And then we know that R is greater than Q by construction, so then R is greater than or equal to 0. It can't be 0, but it's at least not false to say that R resides between 0 and 1. So this thing here converges. How do we know that? Well, because the quantity is an absolute value, smaller than 1. In fact, it's an exercise, but you can show it. This geometric series takes on the value r to the n plus 1 over 1 minus r. The key takeaway is that this is actually a finite number. In particular, what that means is that this series here converges by the comparison test because it is smaller than a convergent series. And we know that it's greater than 0 because all of the terms are positive. So the tail of the series converges. So if I look at the full series, a0 plus a1 plus all the way up to an, capital N here, plus the tail, this converges. I'm adding a finite number of finite values. This whole thing here converges as well. I'll add one more here. I'm going to show what happens if the ratio converges to some value greater than 1. So the ratio converges to Q. Q is greater than 1. Well, as before, you can find some value r, which is going to have to be greater than 1 here, and some integer n, such that the ratio an plus 1 over an has to be greater than or equal to r for every n greater than n. Now this r is greater than 1. What that tells us is that an plus 1 is greater than n for every n greater than n. Well, in particular, then it's impossible for the sequence of ans to converge to 0. In order to converge to 0, these terms would eventually have to converge to 0. What we're saying is that they keep on getting larger after a certain point. So the ans don't converge to 0, and hence, it's one of the results that we've seen, this series does not converge. The proof for the root test is basically the same. One thing to remember in these theorems is that if the ratio of successive terms goes to 1, or if the nth root of the nth term goes to 1, we can't conclude anything, right? If you look at a harmonic series, 1 over n, well, if you look at the ratio test, an plus 1 over an would be 1 over n plus 1 divided by 1 over n, which is n over n plus 1, and that goes to 1 when n goes to infinity. We can't conclude that the harmonic series converges or diverges. On the basis of that test, we know that the harmonic series diverges. But this test does not allow us to say that. Now you might say, well, no, here you've given us the example. Whenever it goes to 1, it's supposed to diverge because the harmonic series diverges when the ratios of successive terms go to 1. Well, what about if you look at 1 over n squared? The ratio of the successive terms would be 1 over n plus 1 squared divided by 1 over n squared, and that is simply n squared divided by n plus 1 squared, which is n over n plus 1 squared, and that also goes to 1 when n goes to infinity. But we know that this series converges by the comparison test. We've compared it to 1 over n times n plus 1. So here I have two series where the ratio of successive terms goes to 1, and yet the first series diverges and the second series converges. And so when they go to 1, we don't know. It's a mystery. I'm going to leave you with two statements which I will not prove. It's not too difficult to prove them. A statement on absolute convergence and a statement on rearranging the terms in a series. If the series of the absolute values converges, then so must the original series. Be careful, this is not an if and only if statement. If the series without the absolute values converges, such as the alternating harmonic series, then you can't conclude that the series of absolute values must converge as well, because the absolute value of the alternating harmonic series is just a harmonic series, and we know that one diverges. The contrapositive of that statement is obviously true. If the series of terms without the absolute values diverges, then the series with absolute values also diverges. And the final theorem on rearrangement: if the series in absolute value is convergent, so we would say that it is absolutely convergent, then every rearrangement of the original series converges. And by rearrangement, I mean that you can change the order in which the terms are added.